Okay, so welcome to this next video in which we are discussing the Sylow theorems. Okay, right. So in the previous video, what we have succeeded in doing is proving the first Sylow theorem, which is the statement that there will always exist a subgroup of order a primed with the highest power that it appears in the prime factorization of the order of the group. Okay, and that's called a Sylow P subgroup. Okay, so in this video what we're now going to turn our attention onto is the second Sylow theorem. Now just before we move on to the second Sylow theorem, I want to discuss something about Sylow P subgroups. Okay, so from the first Sylow theorem then, we have proven the existence of a Sylow P subgroup. Okay, so let's let capital H here be an element of this set of Sylow P subgroups of the group capital G. Okay, what I now want to show you, or just discuss, is the fact that if we conjugate this subgroup capital H by some element of the group capital G, then the subgroup that we get will also be another Sylow P subgroup. So what I want to discuss is that we can construct more Sylow P subgroups by conjugating this Sylow P subgroup that we found by elements of the group. Okay, so if we take little a is some element of our group capital G, what we can now do is conjugate this subgroup capital H by little a. Okay, and we've seen in one of the previous videos in this playlist on group theory that when we conjugate a subgroup capital H by an element of the group, you end up with another subgroup. Okay, and that subgroup is going to have the same order as the original subgroup, so indeed this conjugate of the subgroup capital H is going to be another Sylow P subgroup. So I'll just remind you of what this actually means. So this means go through all the elements of the subgroup capital H and conjugate them by little a. Okay, so take all little h as an element of capital H, conjugate every last one of them by little a here. Okay, put all of those answers into a set, and this is going to be the conjugate of the subgroup capital H under the element little a. And we prove in the video on conjugation of a subgroup that when you conjugate a subgroup in this way, you end up with another subgroup. Okay, and that new subgroup will have the same order as the original subgroup. So in the case of capital H is a Sylow P subgroup, then this new conjugate of this Sylow P subgroup will also be a Sylow P subgroup. So once we've got one Sylow P subgroup, then we can find some more Sylow P subgroups potentially by conjugating the subgroup by little a. Of course, if we're working in the abelian group, we know that conjugation has no effect, so this won't work if you're working in an abelian group. Okay, but if you're working in a non-abelian group, you can potentially find some other conjugates of this Sylow P subgroup, and those will also be Sylow P subgroups. Okay, right. So that's a way then of building more Sylow P subgroups once you've got one. Okay, now what I'm going to move on to is a statement of the second Sylow theorem. Okay, so we're now going to move on to the second Sylow theorem, so number 2 now. Okay, and number 2, when you state number 2, it's the one that looks the most complicated. The statement of the first Sylow theorem was nice and simple. You could understand straight away what that actually meant, okay, and why potentially you'd care about that. The proof then was very, very involved and took us a long time, but at least the statement of the theorem was simple. Whereas the second Sylow theorem, the statement of the actual theorem is quite complicated and looks kind of like, well, why would I actually care? But the proof is less involved than the proof for the first one was. Okay, and we will see why the second Sylow theorem is very, very powerful. Okay, indeed, we will see a corollary of it just after we've proven it. Okay, right. So what then is the statement of the second Sylow theorem? Okay, so once again we're going to assume that we have capital H, which is a Sylow P subgroup of G. Okay, and as I say, this theorem is quite difficult to state, so what I will do is draw a picture of what it actually means. So I'll draw this picture as I go along. Okay, so let's say that this box here represents my group, capital G. Okay, and I'll colour my whole group in orange here. So this is the entire group, capital G. Okay, now let's add on to this picture my subgroup, capital H. So let's say that this portion here is my subgroup, capital H, and it's a special subgroup because it's actually a Sylow P subgroup. Okay, so the order of my group, once again, we'll say that the order of the group is some p to the power of alpha times m. Okay, so the order of my Sylow P subgroup will be p to the power of alpha. Okay, right. So now, what the second Sylow theorem says is that if you have some other subgroup in capital G, okay, so now let K be another subgroup of capital G, okay, and the important thing is that the order of K is a multiple of P, so let P divide the order of this subgroup, capital K. Okay, so the order of this subgroup, capital K, contains some power of P in it. Okay, so the order of K could be something of the form P to the power of beta, let's say, times m bar, where m bar is some portion of m here. Okay, remember, because K is a subgroup of capital G, its order must divide the order of the group. So when we look at its prime factorization, these powers of primes must be contained within the prime factorization of the order of the group, capital G. Okay, so it must just be part of the prime factorization of the order of G. Okay, so beta here is some number greater than or equal to 1 and less than or equal to alpha. Okay, so it's not 0 is the point. There is some power of P in the order of K here. That's very important, that P does divide the order of K. The order of K is a multiple of P. It's not the case that it has no power of P in it. Okay, so let K be a subgroup of capital G such that P divides the order of K. So let me now mark K on this picture. Okay, so I'll mark it on like so. So let's let this be our K, and I've coloured in everything to do with K in turquoise, so I'll keep to that. Okay, so here is K. Now, of course, K and H will have a non-empty intersection because they're both subgroups, so they will have to, at the very least, both contain the identity element of the group capital G. So that's why I've drawn them having a non-empty intersection there. Okay, right, so we've got some arbitrary subgroup of our group capital G, and the only condition that we've got on it at the moment is that it has a power of P in it, in the prime factorization of its order, basically. P divides the order of this subgroup, capital K. Okay, so this now is the statement of the second Sylow theorem. Okay, there exists a conjugate of the Sylow P subgroup here. Okay, so there exists some A, which is an element of the group, such that the conjugate of this Sylow P subgroup by the element little a, okay, intersect the subgroup capital K, okay, is an element of the Sylow P subgroups of K. Okay, so that is the Sylow second theorem, the second Sylow theorem rather. Okay, so I'll underline that in purple, and now we'll draw it on the picture. Okay, so what this says is that there exists some conjugate of this Sylow P subgroup of the group capital G. So there exists some A such that if we conjugate capital H by little a, then the intersection of this new Sylow P subgroup, and after all this will be a new Sylow P subgroup of capital G, we've just discussed the fact that when we conjugate a Sylow P subgroup, we get another Sylow P subgroup. Okay, so this conjugate of our original Sylow P subgroup, which is itself a Sylow P subgroup, intersect the subgroup capital K, is going to be a Sylow P subgroup in the subgroup K. Okay, so to draw this on the picture, let's have it like so. Okay, so let's say that this can represent the conjugate of our original Sylow P subgroup, capital H. So this is representing AHA inverse. And what colour should I colour it in? I'll have it in vivid purple so it shows up here. So here is our conjugate of the subgroup capital H, AHA inverse here. Okay, so you can find some conjugate of capital H such that if you take the intersection of AHA inverse with this subgroup K, now what's that in terms of our picture here? Well, the intersection of the conjugate of capital H under the element little a with the subgroup K is this yellow portion here. Okay, it's the portion of the purple set that intersects with the turquoise set. Okay, so there it is in yellow. Okay, and this is going to be a subgroup of capital K. Okay, we've discussed in a previous video in this playlist on group theory that whenever you intersect two subgroups, you end up with another subgroup of the group capital G, but this is contained within the subgroup capital K, so in fact this is going to be a subgroup of capital K. Okay, so AH A inverse intersect K there is going to be a subgroup of capital K. Okay, and it's going to be a very special subgroup of capital K because it's actually going to be a Sylow P subgroup, basically. Okay, so the order of this is going to be the maximum power of P that appears in this subgroup capital K. So the order of this is going to be P to the power of beta, where beta is some number between 1 and alpha. Okay, and that's what it means to be a Sylow P subgroup of the subgroup capital K. Okay, so that is what the second Sylow theorem says, that you can always find this conjugate of our Sylow P subgroup, okay, which itself will be a Sylow P subgroup, which if you intersect it with this subgroup capital K, which has a power of P in its prime factorization of its order, okay, will be a Sylow P subgroup of that subgroup capital K. Okay, so that's what I meant about how this one is more difficult to understand what that actually means and why you would even care about this. Okay, but the proof is going to be slightly more simple, and the proof is going to give us some intuition as to why this might actually be something interesting to be true. Okay, right, so how are we going to prove this? Okay, well initially what I just want to do is do the setup. Okay, so I want to discuss something with you that initially you might not see how this is going to help us to prove this, okay, but it will help us to prove it. It's going to be kind of like proving that P didn't divide the order of that set curly C that we had to do for the first Sylow theorem. Okay, so I'm going to do a bit of setup and then we'll go in for the kill. We'll use this setup to actually prove this second Sylow theorem. Okay, so the setup then that I want to do is consider partitioning up the group capital G into the left cosets of the Sylow P subgroup capital H. Okay, so that's what we're going to start off with. So let me draw a picture here. Okay, so we'll have our group here, okay, and we've got this Sylow P subgroup capital H here. Okay, so once again I'll colour it in, so we'll have the group represented in orange once again here, so underline it in orange, and then we'll have the subgroup represented in green here, so I'll colour it in green. Okay, so what we can do whenever we have a subgroup of a group capital G is we can use the left cosets or indeed the right cosets of the subgroup to partition up the group. Okay, and it forms a well-defined partition. Okay, now if this subgroup is not a normal subgroup, then the left cosets will form a different partition to the right cosets. Okay, but that doesn't matter. We're just going to take the left coset partition basically. So we've got our subgroup capital H here. We don't know that it's a normal subgroup. It might not be. So we're just going to use the left coset partition and be happy with that. Okay, so we're going to partition our group here up into the left cosets of this subgroup capital H, which remember is a special subgroup because it is a Sylow P subgroup. Okay, right. Let me just remind you of the definition of a left coset. So, for instance, let's take this one here. Okay, this might be the left coset that contains the element little a. Okay, and we could then write it as the left coset of the subgroup capital H under the element little a. So you can pick any representative you like from this left coset, and if you use that element to generate a left coset, it will give you the exact same set. That's one of the incredible things about cosets. Okay, so this subset of capital G will be all things of the form A composed with little h, where little h is an element of capital H. So it just means go through all of the elements of this subgroup capital H and left multiply them by this element little a, and that will then give us the left coset of the subgroup capital H under the element little a. And what's incredible, as I say, about cosets is that you could pick any other element in this left coset of the subgroup capital H under the element little a, generate its left coset of this subgroup capital H, and you'd get the exact same set, and that's why this partitioning of the group up into the left cosets of a subgroup is a well-defined partition, okay, because it doesn't matter what representatives you actually use to form the left cosets, the partition that you get will still be exactly the same. Okay, right, so we will use often the notation for the left coset containing A bar basically. So this notation is a common notation for cosets. You take a representative from the coset, you put a bar over it, and that then means the left coset that contains the element little a basically. Okay, right, and of course you could use any representative you like there. Little a was just an arbitrary one of this left coset. Okay, right, so that's just a reminder of what a left coset actually is, and the fact that you can use the left cosets of the subgroup capital H to partition up the group capital G. Okay, right, now what I'm going to construct then is a set, okay, which I'll call capital S, and this set capital S is going to contain all of the left cosets of the subgroup capital H. So it's going to be a set of left cosets of capital G. Okay, so it's going to be all things of the form A capital H, where A is an element of the group capital G. Okay, so you go through all of the elements of the group, you generate their left coset of the subgroup capital H. Of course, you'll get loads of degenerate answers here, okay, because all elements that appear in the same left coset will generate the exact same left coset. You do not add a left coset in more than once, so if you go through an element of the group and generate its left coset, and that left coset is already in your set S, you don't add that in again, you just add each one in once, okay, but you collect together all of the distinct left cosets of the subgroup capital H, you stick them all into a set together, and that's my set capital S here. Okay, so we put all of these left cosets, in this case it would just be 4 for my picture here, you would put all of those into this set capital S. Okay, right, so what we're about to do is consider a group action by the group capital G on this set of left cosets of the subgroup capital H. But before we do that, let's just consider what the order of this set capital S is. Okay, how many left cosets of the subgroup capital H actually are there? Okay, well of course that's just the definition of the index of the subgroup capital H in the group capital G. Okay, this just means how many left cosets of capital H are there in the group capital G. Okay, well, we can work that out. We saw previously when we were proving the first Sylow theorem a formula that applies in finite group theory for the index of a subgroup capital H in the group capital G. Okay, and I'll just remind you of how you get that. Okay, you get that by acknowledging that the fact that all of these left cosets of the subgroup capital H all have the same order as the subgroup capital H. Okay, so if I want to work out what the order of the entire group is, what I can do quite simply is multiply the order of the subgroup capital H by the index of the subgroup capital H in the group capital G, and that will give me the order of the group. Okay, this says what's the order of the subgroup capital H, and indeed all the orders of the cosets of capital H. Then just multiply that by the number of left cosets that you actually have of the subgroup capital H in the group capital G, okay, and together that will give you the order of the entire group. It must do, because the order of the entire group is just the sum of all the orders of the left cosets, and this is the sum of the orders of all the left cosets. Okay, but what that allows us to do is say that the index of H in G, the number of left cosets of the subgroup capital H in the group capital G, is just the order of the group capital G divided by the order of the subgroup capital H. Okay, so now what we can do is just fill in the numbers for the order of G and the order of capital H. Okay, we know that the order of the group capital G is p to the power of alpha times m, where remember p does not divide m, so there's no power of p left in m. We've pulled out the highest power of p that we can there. Okay, and then the order of capital H, well, it's a Sylow P subgroup, so its order was p to the power of alpha, so this means that what we're left over with is m here. Okay, so the order of the set, capital S, is just going to be m here.